My name is Jennifer Bowman. I'm with Northrop Grumman, and I'm honored to be here to introduce this panel. I would say we have the best panel, but there's a limiting factor, and that's me. But we do have the best panelists, undoubtedly. This is a really exciting time in exploration, and I'm very excited about the Artemis launch coming up this year. It's been a long time coming, but well worth the wait. And at this point, there are no insurmountable hurdles to reaching Mars. We can get this figured out. It just is going to take a matter of our collective will, and the support of the United States and our allies. So there are so many ways to support this vision, and everyone can participate. And today we'll specifically be talking about Mars habitats, and we have a lot of great vantage points at this table here. So first I'll introduce Mike Ellspermann from Boeing. He's a director of exploration. 30 years of technical leadership, and what he wishes he could do is still dunk the basketball.
30 years takes a toll.
Yeah.
Yeah, that's true. Thanks.
All right. Yeah. Mars?
That's great. That's a great idea. I'm in. I'm willing. Well, thank you, Jennifer. I appreciate it very much. Being here today, I appreciate the opportunity to talk about this. This is a really cool time. The Artemis 1 launch is coming up, and I was mentioning to somebody else out in the hallway having a conversation. They said, Mars is always in the future, right? It's always just a little bit further. It always seems to move out, not only for the human exploration, but like for Mars sample return. So the fact that we were actually going to fly the first 2 elements that you need to get to Mars is really a great achievement, and I think it sets a stage for a lot of good things to come. Are we showing charts? Oh yeah, go ahead. Yeah. So just go to chart 3. So basically, I've just got a few topics today, just to kind of get the ball rolling, just to talk about kind of generally what habitation is, talk about the importance of extensibility in common systems when you're doing development of these big system of systems, and then why I think the cislunar activity, both on the surface and in cislunar space, as a proving ground is really, really essential for us to have a successful set of sustainable missions to Mars. Artemis 1, somebody said this year, this August, summer maybe, summertime. I'm sorry.
They will formally set the date after they complete the wet dress rehearsal, and that's supposed to start in early June.
So habitation is really critical. It's an absolutely critical capability for exploration, obviously, right? It provides the long-term living working space for crewed missions. And it's really a complex system of systems. It's not just a habitable volume. It's not just a eclipse system. It's all of the things that a functioning spacecraft needs to keep crews alive and get them where they need to go, and once they're there, to help them stay alive where they're at. And really, in previous, Boeing's been involved in habitation for quite some time. All the early, Mercury, Gemini, Apollo, shuttle, station missions, we've had a role in that. Progressively larger systems, right, and longer duration stays where we're at with Space Station now. We've had people continuously there for over 20 years. That's really quite an accomplishment. We've learned a lot there. But the habitats we're talking about for exploration are kind of a new animal, a new critter. Trying to keep people alive on the surface of the moon in probably the worst environmental conditions, maybe in the solar system, on the South Pole for greater than 60 days. Then to take crews and keep them alive and get them back from Mars on the order of anywhere from 600 to 1,200 days, depending on the mission class. And then once we get to the surface, right, it's going to be a multi-year operation. So those habitats have to survive the environment on Mars for quite a long time. So they're really important, and there's some really challenging requirements that go along with that. They obviously have to ensure 24 to 365 day availability of critical crew functions over the course of the mission. And you've got to do a trade when you're doing a design of this system of systems. Obviously, you have to, for these long duration cases, and when you're far away from the Earth, you have to have very high reliability on those components, or you're going to have a lot of spares. On the previous eclipse panel, the panelists were talking about the trades between mass of the eclipse versus having high reliability. So in the work we've been doing recently on trying to design these habitats for these long-duration missions, mass is really a key. It's super, super, super important. It is like the king parameter. When you get gear ratios of like 8:1 to get to the surface and get to Mars orbit, for every 1 kilogram delivered, you've got to burn 8. You've got to really look and make sure you've got really low mass systems, which minimizes the size of propulsion system, and so it just kind of just ripples from there. Also, when they're on these long missions, both crewed and uncrewed, depending on the application, you've got to obviously have some advanced health monitoring to make sure that your systems are working. And ideally, you've got some capability to do predictive maintenance. If you have a lot of sensors and like sensor fusion, you can tell when things are starting to fail. If you get little weird signatures, either in the rotating equipment or things like that, then the crew can either go take action and replace that item before it fails, or if you've got, if it's uncrewed, maybe you have an autonomous robotic capability to do that. So those are the considerations in terms of the availability of critical crew functions. Thinking about developing these large system of systems, obviously they're going to be very complex, which implies a long development schedule perhaps, and also a very costly development schedule because they are very, very big and very complex systems. I think the key to really make it sustainable is to have an eye towards extensibility. So, and we'll talk a little bit more in a couple charts about starting like at ISS and learning from there, and then any new developments should be extensible to the end goal, which is a Mars surface habitat to the extent it can be, because once again it'll reduce your development complexity. Ideally, you want to envelope your worst case design environments if you're looking for a common design as much as possible for the different applications. And really trying to leverage runtime on the preceding application so you can learn from what the previous design did, where the flaws are, where the strong points are, and you can put that on the design going forward. So I think that's really important. Really trying to look at it like a product line. If you think about habitation, I think that's a good vantage point going forward. One thing I'll also beat on, as the last panelist did, is early development and life testing, really to reduce risk. You can't cut corners. There's the development programs from across human space flight. There's a lot of lessons learned there on things that we might have done differently, or we might have not cut corners, or we might have done more testing, longer testing, both at the component and system level. So early ground-based mock-ups are really good to drive out problems, or to at least better understand the design challenge. And then obviously technology maturation is key. If you have a new capability that you need to start early. You need to make sure it's at the right TRL, and you once again need to get runtime on it. And those demonstrations on orbit in relevant conditions are really important, where the ISS is really strong for that. It's a good place to be. If I had another chart on the screen, I would talk about the commonality across the application. So LEO or Gateway, those are kind of the near-term initial large habitation systems beside ISS. Then there's a lunar surface habitat, right? That's probably going to be the next instantiation, putting on the lunar surface. Try to take as much as you can from the LEO and the Gateway designs to put onto that system. There's also another great extensibility between the LEO and Gateway work onto the Mars Transit Hab. Once again, it's serving a similar function. They operate in kind of similar environments, but the mission durations are obviously a lot longer. And then there's the ultimate goal, which is a Mars surface habitat, right, where the crews are going to go and stay and live, and eventually maybe we'll have a continuous presence that's down the road a ways, but it should what we should be shooting for. So across those systems, I would say you can have, you shoot for interoperable avionics systems across the platforms there. Gateway's doing a good job with the interoperability standards, including time-triggered Ethernet. So you want to make sure that all the other systems can leverage that. ECLSS is a little different, right? So, and you might be able to help me on this. I know the commercial LEO destinations right now, those design trades are ongoing, but I think they're going to be open loop. Is Halo open loop to start with, or is it regen?
Sure.
Okay, I'm thinking I thought it was open loop, but pardon?
Open.
It is open loop? Okay, good. All right. Hey, all right. So that's a common thing between those two. But when you get to like the lunar surface habitat, once again back to mass, You probably, you could do an open loop, but then you're going to have a lot of logistics missions, and it complicates things. You probably want some kind of a partial regen eclipse with your lunar surface hab. Well, but then for the Mars transit and Mars surface applications, you obviously want full regen, and so that's a real critical capability. So you can incrementally learn from once again, from your initial developments and integrate those down the stream. For thermal control, body-mounted radiators are really, really good for the in-space applications. But for those surface applications, you're probably going to have a combination of body-mounted and deployables just because of the environment that you're working in. But once again, you can demonstrate the BMRs, in orbit, and then you can show that you can do you can do a successful deployment of your deployable radiator on the surface of the moon, and then once again extend those into the other applications. Common power, common passive thermal, crew quarters and hygiene, right? That's a kind of a big deal. Zero G. We've got systems on ISS, but they could perform better. Every week at staff meeting we hear about there's a lot of troubleshooting going on with the toilet or the eclipse system in general. So you've got to make those work, and it'll have to work for Halo too. And then taking that system, once you get it perfected for in space, putting it into a gravity field, that changes everything, right? You've got to do some little different design and different operational concepts. But once again, if you do that at Gateway and you do the lunar surface, that should be extensible over to the Mars transit and the surface hab. Exercise is the same thing. You've got to have, keep the crew in good physical shape, so you can use common systems there. And then windows and EVAs and hatches and docking systems and things like that, you should look for commonality across the board. And some of the other systems are all pretty much the same way, but we should look for commonality when we do development of these systems. High degree of common subsystems really supports extensibility. And then the other chart that I would be showing you if it was on the screen is how Artemis is really, this is the thing I'm a big proponent of. Artemis is really a real great proving ground for habitation. In the 50 objectives that got released by Associate Administrator Melroy yesterday for NASA, there's a whole section on habitation and transportation, and she mentioned several times about how important it was to get smart and build muscle and do push-ups at the moon to get ready for Mars. So those LEO, cislunar space, lunar surface are really well suited to do these relevant tech maturation and system level testing tasks that have to be done to verify that you're ready to take stuff to Mars, right? So the gravity's pretty close to the moon, so the moon's really good for that, 1/6 versus 1/3 G. Dust is a problem on both surfaces, but for different reasons. Martian dust is, as opposed to the sharp regolith, which was really kind of a surprise to the Apollo astronauts. Martian dust, I guess, from what we've seen from the rovers, is extremely small particles, very, very small particles, and it contains some somewhat nasty chemicals like perchlorates. So we've got to figure out how that dust environment is going to operate with the habitation system. If we can operate at the lunar South Pole, we can probably cover the temperature extremes.
You're up.
Oh yeah, go to the last chart. Just cut to the chase. Surface temperatures on the South Pole definitely envelope what you're going to see on Mars, so that's a good thing. Radiation, both from a crew and from a electronic standpoint, compared to the ISS, the radiation environment at Mars and the lunar surface is about two and a half times higher than what they see. So we've got to prepare for that. We've got to protect for that. We've been looking at concepts of how you can find space for the crew to survive, and especially when you're on these long transit missions, how you can get them in a safe spot besides just a safe haven. You might be able to use logistics or other components that you bring along to kind of serve as a radiation barrier. The real thing, though, it's going to be hard to figure out how to test this one, is the effect of the Martian atmosphere on the habitation system. And so it's a combination of the dust, but with the winds, right? So you're going to have a very erosive, environment potentially. So you've got to do some real hard thinking and designing on what your materials are going to be, how are they going to withstand that erosion, and also there are once again some interesting components in the Martian atmosphere that we're really not certain how they're going to play with some of those materials. So we really need to get some data back from Mars rovers, and a sample return would be really good. That'd be really good to have, to figure out how we can basically design and develop a comprehensive qual program for for the Mars surface habitat. So those are some consideration to think about when we're talking about habitats for Mars, and using Artemis as a proving ground is really important.
Thank you. Dr. Robert Howard is he comes to us from Houston, JSC, and is the Habitability Domain Lead and co-leader for the Center for Design and Space Architecture. He is a prolific writer with more than 70 human spaceflight technical papers and a sci-fi series. Next year, maybe we can get him to do some book signings.
Good afternoon. We can go to the next slide. So basically, when we're talking about Mars surface, the duration can vary. There are a lot of architectures floating around, so if you pick up one, it'll say 300 days on the surface. You pick up another, it says 30 days on the surface. And there are a lot of factors that go into shaping what constrains a given architecture, so there is no hard and fast rule. So in the old days, we only saw the long stays. Now we're looking at the short stays. You could see things in between. But I want to talk about a range of different options and sort of show some examples of how that impacts your habitation system. For those who are working in companies developing architectures, you could focus on long stay only or short stay only, or you could develop an architecture that is applicable to both. So you might fly Expedition 1 as a short stay and Expedition 2 as a long stay if you design that architecture to support that kind of flexibility up front. Next slide. Looking at the short stay, I'm going to talk about some of our activities at Desert Rats, the research studies that NASA did in the Arizona desert about 12 years ago or so. When you talk about short stays, there's the advantage of you don't need as much infrastructure. You don't have to have as much infrastructure as you do for long stays. But going that route, it reduces your mass delivered to the surface, it reduces your development effort, but it also reduces the performance of your resulting habitat system, so that's got to be traded. You could have a fixed outpost, you could have a mobile habitation system, or some combination. Right now, for the NASA's official reference activity, we're looking at short stays. That doesn't mean that's what we're going to ultimately fly. We're kind of exploring the trade space. More than 10 years ago, I guess when I was in high school and college, NASA was doing a lot of work on the long stays, and now we've been tasked to look at the short stay. So we're kind of understanding that end of the trade space, and that'll allow the agency to understand the difference and make a decision when it comes time to stand up a formal program. But I'm going to talk about what we did in Desert Rats, because that was a short stay system that we tested with the Pressurized Rover. And keep in mind, those of you who follow Artemis and are looking at what's going on now with the Pressurized Rover, this is the version that existed back at the time in the 2007 to 2010 timeframe during the Constellation program. There are some minor differences between that rover and the current Artemis rover, so if you're in the weeds, you'll see some differences. If you're not in the weeds, it probably all looks the same. So back then, we built two prototypes. We called them Cabin 1A, which is the first one, and 1B, which, how original, was the second one. And if you know them really well, you can look at them and you can spot the differences. Otherwise, they probably look like they're the same vehicle to you. So we did 3 field tests where we had crews living in the vehicles for multiple days. In 2008, it was kind of the debut of the pressurized rover concept. This had been looked at in the 60s really briefly, but then they went with the unpressurized rover and everyone forgot about the pressurized rover. If you're in Alabama, it was a museum exhibit at the Space and Rocket Center, although I think it's being refurbed now. Otherwise, people don't know it ever happened. So when we started thinking about pressurized rovers, there was a lot of, what is this? Is it a good idea? Should you even do it? So the 2008 test, we took the pressurized rover and an unpressurized rover and did a comparison where we ran the same mission with both of them. And we proved that the pressurized rover was actually a better system, where we were able to accomplish more science with it within the same time frame than with the unpressurized rover. The crew also had a better habitation experience. In that same test, we also did a 3-day test just to kind of demonstrate the ability to perform in that vehicle for multiple days and the advantages that gave us. After that test, the Constellation formally included the pressurized rover in the architecture, so it came, it showed, and it won. In 2009, we brought out the second rover and we did a 14-day test. We were kind of demonstrating let's see how long we can get people to stay in this vehicle. We also tested a rescue. One of the strategies we were looking at is, if we have 4 people on the surface, let's put 2 of them in each rover. If one of them fails, one rover goes down, we can rescue them in the other rover. That let us get much farther away from the lander than we could with either a single pressurized or unpressurized rover. In 2010, we ran the 2 rovers in parallel. We did 2 different 7-day missions, both of them with both rovers happening at the same time. So we got a lot of good crew data on the habitability of the vehicle since we had 4 different crews working that summer. We got to see how the systems work together as a team. We tried different ways to communicate with them. Bottom line is, we confirmed through that testing that the rovers were a good platform for short-stay habitation. Some things we learned using the rovers. And if you do habitation design, one of the importance of analogs is crew will use them in ways that differ slightly from the way you thought. And it doesn't matter what habitat you're designing, they're always going to find a way to use it that wasn't what you planned. They tended to concentrate in the cockpit area a little more than we thought they would. And it was fine, but it was just interesting to see how often they used the cockpit versus the rest of the vehicle. They could sit down anywhere, but that was the only place there was something that was a traditional chair. There was a bench further back, but still they congregated in the front a lot. We noticed when they're operating it, they would split into 2 roles. One person would do the driving, and the other person would do all of the science observations. And it was kind of a neat split in tasks. I think we kind of stacked the deck, though, because one of the crew members was always an astronaut and the other was always a geologist, so that had something to do with it. But I think even if it had been would have been interesting if they'd both been biologists. I would have liked to have seen that. When they weren't driving, though, they would often use the front as their office area. So they would do their reports there. They would do ground communications there. Pretty much a lot of the administrative type stuff they would do from their cockpit. Now, they did move further back into the cabin. At least some of the crew did. For crew meals, we just had a rehydration station, a water dispenser. They didn't use for this test, we only had the rehydrated food and the shelf-stable food. None of the thermostabilized food. Some of the astronauts said they really didn't want that, not because they didn't like it, but because the zero-gravity packets are messy in gravity. They're messy in general, but in gravity they'd be really messy, so they were like, don't use those. There was a water dispenser under one of the benches, so they would add their hot water there. And most would sit in the cockpit, although some would come back into the benches and sit, and that was kind of interesting to see how crews had different social attitudes. One thing they asked for were airline tables, because we didn't really have a good table for them to put their food on, and that was something that in zero-G is not an issue, but in gravity they missed it immediately. We had stowage throughout the cabin. We ended up adding more stowage as we went along. The lockers that you see on you see it in all 3 pictures, those kind of soft lockers, those were an addition when we went to the 14-day mission. When we originally designed the vehicle, we thought 3 days was the duration, and then scope creep, we added more and more days and looked at 14. There wasn't enough stowage, so we had to add more stowage to the vehicle. That caused some problems because it blocked the hatches, and so for safety reasons, we had to have a clear path to the hatch whenever we went out the vehicle in case they needed to use it coming in. The rovers use suit ports, so they don't normally use the hatch. That's a contingency method. Some of the crew were neater than others. It was interesting just to watch during the mission, and you could see how a couple cabins stayed really neat the entire time. Others, probably if you have little boys and you've seen their bedrooms, look like that. So there was a trash compartment, and we had stored all of our trash there, including human waste. We basically used a camping potty. And the crews would discover that after about 2 days, they needed to remove the trash because the smell had just gotten too bad. Can't really take lessons for that for the flight vehicle because this was an analog. We don't know what you're going to use for filtration and odor control in the flight vehicle. But if you use nothing, it's going to be a problem. So the aft section, they had benches, and they kind of would relax in them, like for movie watching or just relaxing. Couple of the missions, we had a projector, so they could set up a projector and project a video screen onto a deployable screen to watch movies. Other times, they just watched on their laptop. Exercise was in the back. Hygiene was in the back. I didn't really care for hygiene. If you look at the guy who's doing exercise, the toilet's right behind him, so you can see it's in the aisle right next to the beds. We have deployable curtains that can block it off a little bit, but pretty much you get really familiar and comfortable with each other. We didn't evaluate medical care. We had first aid kits, but we didn't really do any testing with that. Let's see. You can take a screenshot of this if you want. These are some of the test reports from our campaigns, and we captured a lot of good data, so it's important. That was a lesson learned from Constellation. If you don't publish papers to write it down, when the next program comes along, the information is just lost. It's like you didn't even do it. So it was good to be able to document what we did and some of the main lessons learned. Now I'm going to move to long stay habitation. Most of the time, I meant to remove that about conjunction class. Some people get confused about conjunction and opposition, and there are a lot of orbital mechanics tricks to create other trajectories that don't neatly fit into each bucket, but long stay habitation is when you're going to be in the Mars vicinity for a long period of time. Normally, we're talking missions that are hundreds of days long. Generally, it's things that are, we don't have any experience with those missions. The longest crew stays right now on the space station are just shy of 1 year. And we could be spending 1.5 years, 2 years on the Mars surface in some weird cases. So depending on your trajectories, you could be on the surface for a long time. If you looked at the NASA design reference missions, those all were long stay missions, typically in the 300-day range. If you go to our standards, like NASA Standard 3001, there isn't much about surface missions or long stay surface missions, period. The reason is standards are written once we have an evidence base to understand what's happening to the body and how to react. We don't know what's happening with these missions, so there isn't a basis to write the standards. Again, there are lots of different ways you can do this. If you've seen lots of artist concepts earlier this conference, so you can see 3D printed structures, metal structures, inflatable structures, multiple modules, one big module. Lots of ways you can do it. I'm going to briefly talk about the Chipia Habitat that was mentioned earlier today. And those websites and YouTube videos are places where you can also find more information about Chipia. 3D printed habitat, I think you all know that now. The mission's going to start in October. We're going to do 3 one-year missions with a 4-person crew living in the habitat. We're going to delay the communication, so it'll be, when they talk to mission control, it'll be just like it was a Mars mission. The Mars architecture team is helping the Chipia team getting the right concepts of operations, procedures, representative activities, so that the crew will experience something that's at least representative of a Mars surface mission. It won't be an exact duplicate. No analog mission is, but it'll be in the ballpark. The primary focus is the food system. We're trying to evaluate and validate what we want to do from a food approach. My area is habitability, so I'm more concerned with how are they living in there, how do they, one of the big arguments we had was how many bathrooms do they need? And so we're going to assess whether we really needed the 2 I said they needed. We want to understand those things because it affects the mass and volume of the habitat. The way it's constructed and the way the test facility is set up, this is kind of a notional viewing of the area. The blue is the actual habitat. We're going to have a mission control immediately outside it. Docked to the habitat is a node structure, and that allows us to dock other elements there. For this test, we're only going to dock the airlock, but we could potentially dock rovers in future tests. And then outside the airlock, there are 2 EVA areas. We've got a big sand pit with Martian simulate, as well as a virtual reality area where they can do different types of EVA simulations. And in terms of the way the the habitat's set up, we've got private crew quarters for each of them, 2 bathrooms, kitchen, dining area, rec area, plant growth chambers, exercise area, medical area, lab area, and a teleoperations area. So coming October, we're going to start getting data, and we'll start to see in a year how did it really work, and 3 years from then, we'll have some really good data to drive Mars surface hab designs. That's it.
Thanks. Thank you. He's not paying me, but his books are on Amazon. Melodie Yashar is from Icon. She's the director of building, design, and performance. Quite the educational background, but what I'll tell you about her, she's of Iranian heritage, likes tiny robots, and wishes she could fly high in the skies and dive deep in the seas without having to come up for air. And we have a telepathic audiovisual assistant in Jared, but It doesn't reach that far. So if you could tell him when to advance the slides, that'd help him out.
Definitely. Thanks, Jared. And thanks, Jennifer, for the introduction. Forgive me for having to look behind me. My laptop died a little bit earlier today, so I wasn't prepared for having to telepathically communicate with Jared. Hi, everyone. My name is Melodie. I'm the Director of Building Design and Performance at ICON. We are a startup based in Austin, Texas, and we focus on large-scale additive manufacturing solutions for Earth and space. On Earth, we build homes, and in space, we hope to build habitats and other kinds of infrastructure to support an eventual lunar as well as a Martian settlement. Next slide, please. As Jennifer alluded to, I have a pretty diverse background. I started out as a terrestrial architect. I was a little bit frustrated with the documentation needs and kind of the general sort of regulatory environment that I was working in. I made a hard transition to doing research in human autonomy systems and human autonomy teaming in particular. And now I'm working at ICON, sort of bridging those two worlds, architecture and human-robot interaction. So today I'm going to tell you a little bit, though, about my background working and designing 3D printed habitats. I was a co-founder of a group that was a repeat contestant and winner within NASA's 3D printed habitat competition, which was a NASA Centennial Challenge that kicked off in 2015 that solicited the general public for concepts for 3D printed Mars habitats. So next slide, please. I'll tell you a little bit, very quickly, about those projects today and how they sort of created an ecosystem where spin-off projects and future collaborations led to things like the Chipia Analog that Dr. Howard just spoke about. Next slide, please. So the key concept when we're talking about and thinking about additive manufacturing in space for the purpose of creating infrastructure and like habitats is this concept of Nc2 Resource Utilization, ISRU. And that's alluding to the fact that we want to use and leverage the local and indigenous materials on the planet. In this case, usually we're talking about Martian regolith as a surface construction material to create landing pads, roads, and habitats, as well as other kinds of unpressurized structures. Next slide, please. The reason we want to do this is that it's prohibitively expensive. I mentioned this a little bit earlier today, to launch all of the systems that we need, including the tons and tons of what I think would have to be cementitious materials into space to create these kinds of infrastructure elements. So instead of launching everything from Earth for a long-term sustainable approach to create a permanent initial settlement on the Moon and Mars, we want to manufacture materials as well as manufacturing technologies to make these elements there rather than launch them from Earth over the long term. Next slide, please. So here's a quick graphic of the 3D printed habitat challenge. It was split up into a virtual design component, which was essentially an architectural competition, as well as construction technology demonstration levels to demonstrate certain capabilities having to do with 3D printing. Next slide, please. These were the minimum program requirements for the habitat competition. I'm mentioning these now so that you know what we were asked to design for. This included functional space planning for 4 astronauts to live on the surface of Mars for 1 year. They give us some requirements. I think Dr. Howard might have been involved in putting together these requirements. I could be wrong. They gave us some parameters for the ECLS volumes that we would need and the systems that we would have to incorporate, as well as some general parameters for the level of development, which is an industry term that's traditional and that's characteristic of building information modeling, for the level of detail and fidelity that we would develop the structural system as well as the mechanical, electrical, and plumbing systems. Next slide, please. Okay, so the first project, this was the phase 1 winner within the 3D printed habitat competition, is known as Mars Ice House. This was a collaboration between two small companies, Space Exploration Architecture and Clouds AO, we introduced a 3D printed habitat made out of water ice that would be enclosed within a pressurized ETFE membrane, such as you see here. Next slide, please. So we took a vertically oriented lander that would house all of the ECLIS components and other mechanical and electrical components and envisioned how we would create a self-supporting ice shell 3D printed around that centralized lander. And again, inside of a pressurized membrane so that the ice doesn't sublimate on the surface of Mars. Next slide, please. The reason we were interested in water ice is because it is a superior radiation shield against, as compared with regolith as well as aluminum. And that to us, even though this was a fairly speculative concept at the time, that to us presented some really interesting value adds in terms of how we can shield astronauts over the long term against radiation. We were also sort of interested in this idea that water as a building material could introduce translucency and introduce a better connection to the exterior landscape on Mars, which you may not necessarily get with opaque building materials. Next slide, please. Here's a view of Mars Icehouse from the outside. Next slide, please. Our aspirational concept for vision windows that can create that connection with the broader Martian landscape. Next slide, please. Hydroponic gardens that we introduced. Next slide, please. I've got a lot of images, you guys. And now I'll tell you really quickly about our second concept that we submitted to the 3D printed habitat competition. The design competition was reinstated with different requirements for materials use within subsequent phases. We introduced a sulfur-based regolith material for this habitat concept, which we called Mars X House, and this won first prize within the Phase 3 competition. Next slide, please. Our approach when we're designing these habitats is to synthesize multiple material, structural, and habitation sort of needs and requirements. So we're trying to synthesize multiple, I guess you could say, parameters having to do with pressure, temperature, radiation, site selection, while introducing and adding a human factors element that would add value to the experience and the habitability of the interior. Next slide, please. Here's a view of X House from the outside. Next slide, please. A rover approaching X House. And part of the work of coming up with these concepts for 3D printed habitats is that we have to not only imagine what the structure is, but how it's made. So if we go to the next slide, you'll see a couple of concepts for how we are going to have to robotically integrate pre-built and pre-integrated components like ECLIS within a 3D printed structure. The whole premise for this type of operation is that if it's really going to happen autonomously, these systems are going to have to coordinate when and placement of windows and doors and hatches are actually going to happen, because we're not going to have people there to monitor these types of things. Next slide, please. Here's a view of the inside of X House. We actually introduced a high-density polyethylene inner layer, as mentioned earlier, to protect the crew against toxic perchlorates that are known to be within the regolith. Next slide, please. A view of the wardroom and leisure area within X House. Next slide, please. And here's a construction sequence that we created, basically, again, showing when certain elements would need to be placed within the structure. We introduced this idea of a deployable mechanical core to create levels and platforms as scaffolding so that we could print horizontally and introduce a vertical structure instead of a single-story structure. And yeah, you'll see the white was the high-density polyethylene first, and then the orange, the sulfur-based regolith around, as well as an egress tunnel, because that's an important component for us when we're talking about human safety. Next slide, please. Okay, last two projects. I'm going to talk a little bit about the program that we're currently supporting that's being led by Dr. Corky Clinton at Marshall Space Flight Center, the Moon to Mars Planetary Autonomous Construction Technologies project. We are supporting that program in developing a single construction system to additively manufacture different types of infrastructure on the lunar surface. Next slide, please. We're focusing first on horizontal construction, so elements like landing pads and roadways, and eventually we'll be working towards vertical construction and the creation of habitats. Next slide, please. The considerations when we're talking about lunar habitats over the long term, not necessarily only short-stay missions, are similar to Mars. They're analogous to Mars. So we're thinking about radiation. We're thinking about how to mitigate extreme temperatures. And then on the moon, micrometeoroids and seismic activity. Next slide, please. And I'm not going to go too much into detail on this. These are just some design strategies for how to mitigate against each one of these risks. Next slide, please. We had a concept for a lunar habitat similarly to Mars X House that was a vertically oriented habitat that we introduced for this project. Next slide, please. So you'll see here the Icon printer, which is printing what the project which is referred to as the Lunar Lantern. Next slide, please. Here's a view of the inside of the Lunar Lantern. View of the crew quarters of the Lunar Lantern. And last but not least, I'll end on our recent project, the Chipia Analog, which we 3D printed at Building 220 in the Johnson Space Center. This was a project that, in collaboration with NASA, we were, given requirements and given some general parameters for how this analog should function and how it should be designed. And we were the ones who deployed our printer there and printed it. Next slide, please. So this is the floor plan of the analog. On the far left, you'll see the 4 individual and private crew quarters. In the center, there's a leisure area, and on the far right, there's a working area, a robot simulator room, a medical room, and an exercise room. Next slide, please. Here's a photograph of our system, the Vulcan, deployed at the site. This is a gantry-based robot. It's over 9,000 pounds, and it deploys on rails. Next slide, please. And so here you could see the Vulcan 3D printing the habitat itself. We're using a cementitious material, mortar-based cement material to 3D print our structures terrestrially. In this case, we happened to incorporate a dye that was added into the dry mix of the concrete just to make it look more Mars-like. The roof was actually something that was printed separately and then craned overhead and placed on top of the walls. Next slide, and that is it. Thank you very much.
Thank you. And last, Major Ellie Morgan is with Lockheed Martin. She's the Lunar Exploration Campaign Habitation Program Manager. I asked her what superpower she would want, and then I realized she doesn't need a superpower because she's superhuman. She's a runner. She's completed 2 races at Pikes Peak. She's a pilot. She's completed a 6-week sleep deprivation study during an isolation experiment in Hera. She's done it all. So,
to be fair, we've all completed an isolation experiment now, the last 2 years. But yeah, so thank you, Jennifer. I appreciate it. And yeah, thank you all so much for having us here today. I'm really excited to talk about this. Habitation is near and dear to my heart. And similar to what Melodie was saying, I'll give a quick little background on me and kind of how I got to where I am and why this is really cool for me to be here talking to you all. So I kind of have a non-traditional career journey. Started off my career in the Air Force as a pilot. I transitioned. out of the Air Force, had the opportunity to be involved in human spaceflight research at the Johnson Space Center. So right next to the Chipia Habitat there, they have another habitat that crews have been doing isolation confinement experiments in. So that was a really great experience. Got to be in that with 3 other folks for 6 weeks. That was back in 2018. It's really nice to have the experience on the inside of a habitat being there and then move into a role after that to being a crew systems and systems engineer at Bigelow Aerospace, designing habitats for people and understanding what it was like on the inside. And having been on the operational side of things in the Air Force too, that was always really important to me when I transitioned into the aerospace sector, was to be able to help bridge that gap between the engineers and the end user, because oftentimes when that human factors element doesn't come in, you have a subpar product. And that's very frustrating when you're trying to execute a mission. So I spent some time at Bigelow Aerospace. That's how I met Dr. Howard. We did some human loop testing there. That was a really great experience. Moved on to Lockheed Martin. And next slide. And so what I want to talk to you guys about today is I want to talk to you about some of the projects we're doing at Lockheed Martin and how everything we're working on now with the longer term vision of getting us to Mars. When I first started off at Lockheed, I was involved in some of our mission architecture work that we were doing on a NASA research contract, which I'll talk about more here in a few. And then I went on to manage our Lunar Rover project, which I'll also talk about more here. And then I've moved on to manage more of our habitation projects, and then also our Starlab program, which I will also touch on. So next slide, please. All right. So some of you may or may not have heard about the Commercial LEO Destinations Free Flyer program. Lockheed Martin, we are part of a team. End of last year in December, we got awarded one of 3 awards from NASA to begin development for a commercial space station. And we are partnered with Nanoracks and Voyager Space. So this is a really exciting project that we're doing and bringing together. We're doing a unique approach now on a commercial space station. So it's not all funded by NASA. A lot of this is private funding, commercial funding, and it's our opportunity to, create a new station that will one day replace the ISS, and the ISS will transition over to that. So that's a really exciting project that we are working on right now. Right now, we probably about late 2027 is our estimated launch date for that. So we hope to not have a gap with any human presence in low Earth orbit. All right, next slide. All right. So some of the other important things that we're doing at Lockheed Martin, as many of you are well aware of the Artemis program, the Orion Spacecraft, Lockheed Martin, we built that, and we're really excited to see that launch here soon, hopefully this summer. But the Orion Spacecraft, just for some data points, so that is designed for crew for 21 days, and that is an open loop eco system. So it's kind of a little small habitat. So that's a great way for us here to kind of start off in a small realm with the habitation once we begin the Artemis program. Next slide. Okay. And the Orion will be eventually then going out to the Gateway, which is in cislunar space around the moon. The Gateway, as many of you may know, smaller than ISS, bigger than the Orion, also open loop. And so that's going to be a wonderful opportunity for us to learn more about what it's like to habitate outside of low Earth orbit, which is going to be really important, especially when it comes to, when we've talked about here, what radiation. That's going to give us a more clearer picture of the actual radiation the astronauts will receive on a trip out to Mars, where we're more protected in LEO. So we're excited to be involved with the Orion, and then we also have a team at Lockheed Martin. We're working on the human landing system. There's some more contracts that are underway in development going on, so we hope to also be part of a team for a follow-on lander on the moon. Next slide. All right. And some of the other work that we're doing at Lockheed Martin, we've been involved doing a Next Up Appendix A research contract with NASA now for over 5 years. And we've been doing, what's involved with that is surface habitation, concept development, and then also orbital, and then Mars transport. So it's really given us a great opportunity to work on some designs for the lunar Martian surface, and then also come up with concepts of the extensibility part of that is using that habitat, getting to Mars. We'll talk about it more here, and Mike touched on it, the importance of mass. If we got to take all of our logistics with us, everything we need to go to Mars, how are we going to make that happen on a long journey? How do we design a spacecraft, which I'll show here at the end of the slides, that has enough volume for everyone to not go crazy, but also has enough space, to store everything you need to take it with you. And so that's been a really great experience we've had, and learning more about that, and we're applying a lot of those, lessons learned and the data we've been doing to our Star Lab in LEO, and so extensibility really is the key. How can we build a habitat that we can adjust only slightly for different types of mission sets? Next slide. All right, one of the other key things I just want to touch on that we're doing is we are now involved in lunar mobility. So this is a really exciting new venture that we are now doing in partnership with General Motors and recently also now MDA. And so Lockheed Martin, this is separate from NASA. We hope to work with NASA on the mobility, on future projects with them. We are going to be looking to sell our mobility services on the moon, so kind of think of like a lunar Uber. And but we are going to have some, the importance here is the extensibility of these mobile platforms that we can use, whether they're autonomous or they're for an Artemis crew one day or any other private or commercial astronauts to be driving on the lunar surface. But also, they could carry large payloads. Maybe you put some type of a habitat on there or some other large structure that you can move around. So we think, mobility really goes hand in hand with any type of habitation that you're going to do on the surface. You need to have both. You're going to be doing science exploration. So that's really going to be an important key. Next slide. All right. And this is kind of another cool concept here, but, touching more on the discussions that Dr. Howard was having about, pressurized rover, yes, that's absolutely going to be a really important element too. And I think I don't think it's ever going to be one or the other, a pressurized rover or a surface habitat. I think at the end of the day, we're going to have an architecture that has all of these elements. And really, it's going to come down to what is that crew doing? Like, what does that mission require? And how long is the mission? These are all things we'll talk about more in the Q&A. But, a lot of different requirements obviously will drive different types of architectures. So there's room for everyone. But this is going to be really important too, because we'll be trying to figure out, the ecosystem for this, all right? Well, maybe it's going to be bigger than something or similar to an Orion, but, might need to be smaller than, for a larger habitat as an open loop, closed loop. So a lot of trades are going on now and things that we're all looking into. All right, next slide. All right, and here we have a picture. This is our updated concept for our nuclear thermal propulsion transporter that we have a vision of for bringing humans to Mars. And as you can see here, we do have our updated, this is called Mars Base Camp. We recently released last fall a new version of this. And so we now have an inflatable habitat within the architecture here. We also do have a metallic habitat that is underneath the fuel tanks. They're the gold fuel tanks that is inside of that and for radiation protection. But a lot of exciting things. We have Orion on here. I mean, obviously there's a lot of interesting things. We will continue to refine concepts, and figure out what makes the most sense as we move forward for bringing humans back to Mars. Okay, next slide. All right, and last but not least, this is kind of one of my favorite quotes, and I just feel like it's so pertinent to what we're trying to do today. We all know that space is really hard and it's really expensive. And so as we talk about bringing humans to Mars, absolutely, you cannot do it alone. And so I think one of the things we've been exploring is unique partnerships. I think there'll be a lot of, public and private partnerships, various countries coming together. So, those are things that we're beginning to explore now, and some of the unique projects we're doing on the commercial side at Lockheed Martin. That's not the traditional way we used to do it, but this is, I think, really the path moving forward. And so we really look forward to working with many other partners and entities and the government moving forward to make this dream a reality on Mars. So with that, come join us at Lockheed. Thank you.
Thank you. All right, to kick it off, just a break from your slides a little bit, I'd like you to envision your ideal habitat and just tell us a little bit about what the needs and wants you have for an initial habitat. How would it look? How would it function? Do you want to go first, Ellie?
Oh, okay, yeah. That's okay. Well, it's one of the first things that comes to my mind, having lived in one for a bit, is it's really the importance of having enough space inside a habitat that everyone can have their own private space somewhere in it. I think that's going to be absolutely critical for folks, for many reasons. But having your own space, I think, is going to be important. But I don't know if we're going down the line of different types. Okay, that would be a key thing. Many other things, but that would be a key thing.
Yeah, I was going to say making a hard distinction between shared space, private space, and public space. And in particular, I would also stress that even though there are certain activities that we want to design and provide space and accommodation for, we also have to factor in things like leisure, free time, space for the astronauts to have a little bit of room and customizability so that they can feel like they're an active participant in their environment and it's not something set in stone. So something adaptable, configurable with flexibility would be what I would say.
Thinking about how to answer this, I think I'm going to cheat and say, look up my papers on the common habitat or the deep space science vessel. Those are my two ideal habitats. But to answer the question, I'm going to go in a little different tick. And I'm going to say I want big, big, big launch vehicles, because when I put the stuff I want in the habitat, most of the launch vehicles today can't lift it. So I want bigger beasts to put them into space.
Are you talking about a 10-meter fairing, maybe?
Actually, I might get bigger on you.
Okay. Challenge accepted.
We can work on that. We can work on that.
With better propulsion, too. It's the other half.
So let me see. Obviously, all the comments from the panelists, I agree with. You want to have plenty of habitable space, the ability to feel like you have some privacy. I'm thinking about, and your presentation was really, really cool, very impressive. Having some big windows to be able to see the landscape and interface with it. I think that, the windows we have on, on ISS and the cupola, and then where we're, putting on some of our designs, everybody's thinking, well, actually on the CLD, they're pretty big, but I mean, yours were, the whole thing was a window, so that's pretty appealing. Obviously, a toilet that works, really crucial. And in the spirit of, if Chris is in the room, you probably would want to have a bar. Right? That's for Chris. Yeah.
Chris knows. Okay. I think it's interesting that most of the responses were around usage. You didn't say 8-foot tall ceilings, or it was about spending time and the human interaction with the space. So that's telling. Mike, how has what we've learned on the ISS prepared us for the Moon and Mars habitation?
Yeah, that's a good one. Obviously, the ISS is a national treasure, great asset, a great investment. We've learned obviously a lot about human physiology and how humans respond in zero G. That's important on getting to Mars. It's also serving as a technology test bed for some of the systems that we're going to need to actually have people get to Mars and stay there. And I think that's going to continue to, it's still going to be a continual place to go do experimentation and get more data, to back to your point, getting more data on how the real world affects the crews in space. From a surface standpoint, I don't know that it's really helped that much. We have, one thing we have learned to do is how to operate. So maybe not so much for Mars, but like a gateway, we now have a routine capability to transfer crews and transfer cargo. And it's becoming more, we've got private missions going. So I think that may not be directly applicable to surface habitat, but I think we've learned a lot on how to do that, and also how to start maybe an economy in space, right? Well, that's a good thing. in addition to the stuff at Space Station, obviously we've done some ground things. Ellie, you brought up the next up Appendix A, so we're doing something with the
Right.
folks at Marshall, the Habitation system there too. Doing mock-ups and architecture studies, looking at how we can take there may be opportunities to take some things we learned from our ground work and do demonstrations on new materials on Space Station and things like that. So I think there's still a lot that can be done, but we're in a much better place than we were 20 years ago, for sure.
Yeah. All right, let's talk some more about analogs. Robert, what have you learned in your experiences about the volume of a space and how maybe circular versus square space has an impact on the crew?
Okay. So first about volume, I learned that the charts were all wrong. I kind of knew that anyway. But if you've seen those charts that say volume as a function of number of crew or number of days, throw those away. Volume depends on function. So crew size does matter, duration does matter, but function is what really drives the volume. So you need to identify upfront what are the crew going to be responsible for doing, what kind of equipment's associated with that, and then you can configure it in a way that tells you how much space you really need. Now, in terms of the square versus circular, vertical versus horizontal, we like to live in rectangular buildings. You can see that everywhere. You can't necessarily do that in a spacecraft all the time. Pressure vessels want to be curved. So there's always an efficiency that you have to address when you're trying to lay out a spacecraft. Depending on what your constraints are, small diameter vehicles, you have more curvature issues than with large diameters. Horizontal versus vertical, it really is case by case. You really kind of need to, if you have the option, you want to lay out both. For instance, let's say you're constrained to using a diameter that fits within a particular launch vehicle. If you can, you want to design both vertical and horizontal and trade them. Depending on your functionality and depending on your diameter, sometimes the vertical and other constraints, sometimes the vertical will be slightly better, sometimes the horizontal will be slightly better. It's not a one-size-fits-all. You kind of, that's the kind of big lesson too. You have to test. You can't reduce space architecture to a series of formulas. You've got to go case by case, build and test it.
Okay, good to know. Ellie, how are analog situations or simulations helpful in designing?
Yeah, well, I think they're really helpful because you can come up with a great concept, but then you don't know ultimately how people are going to use it. Like Dr. was saying, well, we thought they were going to do this, but they use the other half of the vehicle. And so I think that's really important piece of it. I know both when I was involved with the analog mission and then also when I was on the other outside of it, in charge of a human-in-the-loop testing, we had people wearing sensors at the time, and we were tracking their movement through the habitat to really understand where are people congregating, is this an efficient use of space, do we need to rearrange things, because as we said, if you only have so much volume, you want to use it efficiently, and so that may help you adjust things and lay them out differently. And yeah, I think with the analogs, obviously getting firsthand inputs from the human-in-the-loop testing we did with the astronauts, that was really helpful. But then, but they were only in there for a finite amount of time. But then when you have people in there, like especially with the upcoming one, for a year, that's going to give some really good data. And all of the Hera missions that they've been doing, ranging up to about 6 weeks, this is really useful data too. But I also think that, the other thing that we can leverage on the habitation side, just in terms of outside the aerospace industry, is like tiny homes is a thing now. Like people using RVs, right? Like there's all kinds of other, analogous types of situations that we can look at the habitation. Or some of the things that I've used over time was how things I did when I was deployed, like when you're far from home, you're executing a mission, you're feeling isolated, all those things, like how do you interact with your environment and what's really important to you. And I agree, I think really it's, what do you need to accomplish? How do you lay things out? You can only put so many things in Habitat, so you got to prioritize, but making sure that things are very multifunctional is really important, like changing a space up or putting a table down. Okay, well now it's a leisure space. Okay, well now it's a writing desk. So I think that's, obviously we have to be efficient with our space usage. Yeah.
You. Melody, with the competition work that you did and with Icon now, what kinds of assumptions are you making about the site preparation? Like, how do you know that, or plan for the ground supporting whatever structure you're going to put on it?
It's a great question. We're making quite a few assumptions, is the fact of the matter. It's always preferable to just assume that you have a level, compacted site ready to build on. And our focus really is on the construction technologies and not on things like excavation or compacting soil. I think that on the moon and eventually on Mars, we're going to have an ecosystem of technologies that are going to have to establish these types of needs prior to construction of unpressurized shelters and then eventually habitats. So things like power and even things like water, like these are all resources that we have to have established and systems set in place to actually be able to even consider have people the land and live in these potential habitats. So there's lots of systems integration to think about before we can even consider building or launching crews there.
Yeah, that construction aspect to me is just fascinating. I think we've got a lot to figure out that we don't even know yet. Robert, how much autonomous building is ideal before a crew arrives?
All of it. I mean, really the crew. Let me rephrase this. As we currently envision human spaceflight, the crew is typically a scientist or a tourist. They're not a construction worker, so we didn't send them into space to build. So ideally, when they arrive, the habitat's ready to go, or other surface infrastructure is ready to go for them to use to conduct their primary mission. So really, you want it to be as ready as possible. Now, one day we might have a future off-world construction industry, and it's someone's business case that they put things together, but unless we're at that point, we really want it fully autonomous.
Do we have robots too that move their stuff in, like the tables and the chairs? And, like,
Ideally,
there's
yes.
a lot to do.
I mean, yeah, you really would want to minimize the amount of work the crew needs to do to prepare their habitation environment.
They're a little overqualified to be movers, I guess. Or or solar panel washers. I don't know. Yeah. Well, Mike, we don't have any samples of Mars regolith yet. What can we do in the meantime?
That's a good question. I think we have to take the available data that we have from our rovers that have been exploring the surface there, and try to extrapolate some type of a environmental model to start with, for sure, and then potentially develop some type of a simulant. If we really want to do in erosion, I think erosion worries me. If we really want to do some testing like that, we could probably come up with a similar material that would maybe give you the same results from an erosion perspective, but the chemical composition of the soil is really the key in how that's going to interact, especially in 1.6G and in a very low pressure atmosphere. I'd start down that road. If we're going to do some early testing, that would be the thing to do, I think. Nothing better than a sample, though.
All right.
I'd agree.
Are there questions from the audience? Because my watch is telling me to stand up.
Hello, my name is Aon McNeil. I work in multifamily earth architecture, but I have a question for Melodie. So I really loved that you were letting in so much light with the ice structure, and I was wondering if there was going to be any coating on the exterior or an element in the ice as a polymer to keep the dust from sticking, or if eventually would it all turn red and then keep building until you can't see anything, it's blocked out.
It's a great question. A lot of times, even when we're thinking about windows and ports and this type of thing, like the dust always becomes an issue. So perhaps we need window washers. But for the sake of for the sake of Icehouse, ETFE, I mean, terrestrially when it's used, does not typically attract dust. It is largely like it looks pretty good when it's constructed here on Earth, and it's a very, very smooth material too. Frankly, I think that if we, and we did, in a future study, we worked with a group at NASA Langley to explore material options for a translucent pressure membrane. ETFE is not an appropriate solution, we later learned, but I do think that there is additional material science research to investigate how we can achieve like bladder and restraint layers through materials that can also be translucent and let in more light.
Thanks. Hi, question for anybody, but maybe primarily Dr. Howard. If you could go back to the design phase for the International Space Station, what would you change, I mean, to make it a happier place to live?
So I was in high school when ISS was being built, so I don't know all of the issues they had, but I do remember reading how Congress would vote on whether or not to terminate it, and they would cut the budget, and they'd have to redesign it every year. So the station we got is not the station that the engineers designed. So more so than the station, I would change the political campaign up to the station. Because I think if they could have built the station they wanted, it would have been significantly different. Now, me personally, I would have built a rocket called the Sea Dragon. It could have launched the entire station in one launch. So. That would have been my action if I could go back in time.
You know, I'll add to that too. The station, it went through many design iterations. I wasn't involved in the design up front, but I did work on the shuttle, and I know that the components were designed to fit inside the shuttle cargo bay. So you had a really strong constraint. You couldn't go any wider. You couldn't go any longer. The modules had to be what they had to be, except for the ones that go the Russian launched pieces. So that was kind of an artificial design constraint. I will tell you today, for the transit habs and the habitat systems we're looking at now, much larger volumes than 4 meters. Doesn't have to be a lot. We've looked at a range up to 7, 8, 10 meters. To your point, the smaller they get, the radiation or the radial problem gets in. But there's a sweet spot in there that is currently, with the launch vehicles that are coming online, we'll be able to launch more optimal diameter modules in the future. I think that'll help too. Also, I think back to testing and qual, I think a more robust and a more in-depth test and qual program probably would help too, especially from all the system maintainability issues that they've had. Another lesson learned.
Thanks. I could listen to these guys on and on, but Chris tells me we have time for maybe one more question. I saw one up here.
This is for Dr. Howard. The habitat, the Chipia, is huge. I mean, to me, it's huge. I led the study for Boeing for a lunar habitat back in the Constellation days, and we were constrained on how much volume we could use. So how did you decide, you already talked about it a little bit, but what other factors did you decide to get so much volume for 4 people? I mean, that's like a 3,000 square foot house, right? That's what it looks like.
We argued extensively, and I was of the camp saying it's too small. There were other people saying it was too big. And now that we're actually outfitting it, people are realizing it's too small. So the issue is functionality. When all you think about is 4 people going to sleep, waking up, doing hygiene, and going back to sleep, it seems like overkill. But once you start looking at a year's worth of logistics, once you start looking at science activities, medical activities, maintenance activities, psychological health, it stacks up, and you start to realize that you needed a much bigger volume than you originally thought. A lot of times in the early studies, and I saw this in Constellation too, the early high-level studies, they love to use parametrics, and they love to use really high-level assumptions of crew tasks. And it's the computer science principle, garbage in, garbage out. Those algorithms really don't cover the details, and so they give you an answer that really won't work once you actually try to implement it. Oh, yeah, yeah, definitely.
Yeah. Well, and I just want to toss in there too. I mean, I think the other important thing to think about is it a surface habitat or is this an orbital habitat? Because, well, you're only going to use like half the amount of volume, you know, in a gravity environment. So yeah, that definitely plays into making it larger as well. Yeah. Right. Okay.
Well, one last thank you for our panelists, and then we have 10 minutes to get back to the auditorium.